Just to introduce ourselves, my name's Randy Province. I'm a data engineer at FedEx in aircraft engineering. I've been with the company for 28 years. Most of that time has been in IT. David Taylor is also going to be doing presenting, and he is a data scientist. He's been with the company 3 years. We're going to talk about applied predictive maintenance, basically the removing of components from the aircraft before failure, or just before failure. And the title is Without Sensor Data, and we'll explain that here in a minute. Basically about our organization, our agenda for today, my name's Randy. Our organization, and I'll be talking about the organization and the mission, and also about the data pipeline and the data models we've built to use this data for predictive maintenance. Dave's going to be talking about the machine learning portion of this and the applied science basically to our data. So basically about our fleet, we have 410 wide-body aircraft. We have we ship about 16.5 million packages daily, and we have 261,700 flights per year. Just to give you a little context. And this is our entire trunk fleet. We have feeder fleets also, but we do not maintain those. We're not responsible for their maintenance. They're contracted out to other carriers to maintain those aircraft. Basically, our organization, in 2014, our CEO, Fred Smith, and founder, they all came to, and upper management came to realization that our fleet of aircraft were aging beyond what they were designed to fly. And we were purchasing brand new 777s, Boeing 777s and 767s, but we were not getting those fast enough for our demand and lift, basically. So for that reason, and for the aging aircraft reason, we were hitting new problems that we'd never hit before, and our reliability of those aircraft was diminishing, basically, and so our reliability was going down. And by reliability, I mean delays in aircraft departures, on-time departures. And so our mission, our mission basically of our team, they formed this team back in 2014 from a variety of different groups. I came from IT, and I worked on aircraft maintenance systems for about 25 years before this. And also we have people, material specialists and component repair specialists on our team. We have aircraft engineers on our team. We have aircraft mechanics, former aircraft mechanics on our team. So it's a diverse team and roles. And we formalized that, after we had some successes, we formalized that team a few years ago and create a real team in aircraft engineering, basically. And our mission is, like I said, to prevent aircraft departure delays. And a delay, basically, if you think of a passenger carrier, if you have a delayed departure, for an hour or so, you could interrupt and pretty much tick off about, maybe up to 300 or 400 passengers on that plane. But one of our 777s could be carrying up to, 100,000 packages, where you've angered over 100,000 customers in just one delay. So it's very important to us that every aircraft leave on time. And with our aging fleet, and then COVID hit, we actually had to start pulling MD-11s, our older planes, MD-11s, MD-10s, and older Airbuses out of storage, out of the desert. And these were some of our worst planes for reliability. So it became a big challenge for us to maintain a high level of reliability for our fleet. And so, like I said, our goal is to prevent aircraft delays. The way we do that is we move unplanned component failures to planned removals. And we developed methods of predicting those component failures without telemetry data. We have telemetry data on our newer fleets, on our 767s and 777s. We have a lot of telemetry data. But our older fleets, our 40-year-old planes, they do not have a lot of messages coming out of them. And they do have some, and we use that, but we have to rely more on our history that we know of that we've been maintaining the fleet for all these years, so the last 30 years or so. So we have to rely more on that than IoT devices, basically. So how do we do that? How do we make this problem? We had to create, about 4 years ago when Databricks joined with Microsoft and Azure, and we were already in Microsoft Azure space, we developed a pipeline to move that data to Azure Databricks. And we started playing with Azure Databricks and really saw the potential there that we could use it for. So we're pushing data from our data warehouse daily, and that is pretty much flush and fill tables mostly. And that's all our component history, our flight schedule data, our aircraft maintenance log history. All that data is being pushed daily to and that's kind of our the bronze data. We also have telemetry data coming from our AirCom server, which is ACARS data, which is telemetry data from an aircraft. And they're small messages, and they could be indications of problems, or they could just be reports, like a cruise monitoring report. That data then goes into our storage account daily, and then the stream data goes in there a few times a day. We batch it up and then stream it to the Azure. And then we, excuse me, we go to our kind of our silver data phase, where we're starting to transpose a lot of and derive a lot of values out of that data. We're also merging, we're scrubbing that data. There's 3 different systems that maintain the aircraft history, aircraft maintenance data throughout, our history of the company. So every set of those history has a different state of nature and a different way of doing business. So we have to merge that data in a way that would be similar and be like. And so, and then we get to, in that silver data, we also push data to Azure SQL Server, where we've written our own system for analysis of reliability type issues. And we also, then we produce to the gold standard, where we do we do component removal predictions, and we also, excuse me, we do that with Power BI. We mostly show that in Power BI and in our homegrown system, Torch, where we use that. And so we use 2 sets of prediction models. We have 2 different algorithms for our predictions. We have one that's just straight business rules, and that's on the next slide. Basically, our business rules, we evaluate approximately 350,000 unique serial numbers installed on the plane. Can you give me some water? I'm about to go through. But sorry, I think that's empty. Yeah, I'll just take that. Oh, thank you. So where was I? Yeah, so we're evaluating 350,000 unique serial numbers twice a week, and we're using business rules to predict whether they're at risk to fail in the near future. And these are only serial numbers that can be removed and that we do fly to failure. There's a lot of components that we cannot fly to failure. And so those, something like that would be a part out of its family average on wing time. So if the family of those parts flies, 30,000 hours, but yet, thank you. And man, my mouth got dry. And, And that part's been on there for 40,000 hours, and we know that they usually fail pretty quickly after that. We will set up the time when it's most cost effective to remove that part and remove it before it fails. We also know, we have a pain index, it's not on here, but basically it tells us what components cause the most delays. And so when they fail, we have an index automatically that's telling us, yes, these are the worst ones, the worst performers as far as causing delays when they do fail. And we use that, and how much it costs to repair them. And David's going to talk more about the money here in a minute, but the money side of it. But we make an evaluation for each component automatically, this is all automated, to whether it's cost effective to remove that part now or not. We also have a set of machine learning algorithms that evaluate 126 different part families. And we're increasing that every week just about. But those 126 part families are the most delay causing parts. We attack those first. So basically each rule, when we get to the end of this, we have one database, one table basically that has all parts at risk and why they're at risk. But are they based on the machine learning algorithm? Are they based on our business rules? And then our analysts can review those and take action and to get those parts replaced. Here's our performance so far. And basically, we were doing this in a SaaS system before 2019. And before that, we couldn't do a lot of volume, especially with the machine learning part of it. It was an on-prem server, and we would pretty much use up all the compute power on that server. And so that just wasn't realistic what we're trying to do. So when we moved to the cloud, our numbers shot way up. If you see that blue over there, that's components that we have not been evaluated yet. All these components get removed. When they get removed predictively, they go to a repair vendor. The repair vendor determines whether it was a confirmed failure, whether it really needed to be removed, and puts out their findings. And when the component returns, we review that data and use that as input, feedback loop back into our processes. And also, we would be removing a lot more parts. We forecast a lot more parts at risk, but we are constrained by our inventory of components, especially on our older fleets, MD-11 and MD-10s. There's not a lot of brand new components out there for those, and not a lot of operational components out there for those. So that's really a constraint because we still have to maintain that those parts do fail. We're not going to find every part that's going to fail. You know, we're not going to get near that, but we're just making it better. But we cannot use up all our serviceable spares and not have anything to replace it. So that's a big constraint that we have. That's basically this part of it. I kind of set up why we're having to replace these parts for reliability. Now David's going to talk to you the how and the financial aspect of it. I'll take both of these waters.
Thank you, Randy. As Randy said, my name is David Taylor, and our main goal is to predict when parts are going to fail. That way we can remove those parts on a scheduled maintenance so that the planes don't have delays, which cost us thousands and thousands of dollars. And that way, planes fly on time and you receive your packages on time. So we want to make our customers happy. And the way we do that is without sensor data. So why don't we use sensor data? Because if you've probably done a predictive maintenance lookup, you've probably seen many examples that says telemetry data, sensor data, machine learning with sensor data. Well, we have an aging fleet that has limited sensor data. One of the issues with sensor data could be labeling. Well, we have these trends, we're seeing this analysis, but does this mean it's going to cause a failure? So we need to have that feedback loop to know that these are actual failures. So one thing we do have is we have a rich history of these parts. So most of these parts are repairable, so they have a multiple life cycle. We know when the part was brand new, when it was installed, when it failed, what age of that part when it failed. where it was sent for the next vendor to repair that part, where it was installed, what position, what aircraft. So we have these rich set of features that describe the nature of this part. And to analyze these parts, we're using survival analysis. This is a common technique used in economics. You may have seen customer trend churn forecasting. You may see loan default predictions. So it's the same type of analysis that it's also used in healthcare for like how effective is this cancer drug? When is a potential end of life in a cancer patient? So, and for our parts, they exhibit a similar behavior known as a bathtub curve. So this curve represents the failure rate over time. Early in life, you have high failure rates due to infant mortality. Bad parts get put on planes, sometimes they're lemons. They fail early in life, they come off. This is followed by a period of just random failures. So the failure rate's been constant. This is the trough of the bathtub. Then followed by an end-of-life failure rate where failures begin to increase in time. And this increase in failure rates is at the end of life is where we're trying to model. This gives us an idea of when the part's gonna fail, and this is where we're trying to model and to predict to do preventative maintenance. And our survival analysis not only gives us a time till failure, but also gives us a survival probability that we use in our financial calculations to determine when and how cost effective it is to remove this part. Now we can remove lots of parts from our aircraft and reduce delays, but our maintenance costs can skyrocket, so we don't want to do that. Our managers wouldn't be happy with that, so we have to make that balance between removing predictive early and also being cost effective. So we use this rich history of data, this part data, and we try to back test these models with a small sample of our parts. We have probably 3,000 different family of parts that we can actually model. So with our small sample of just 126 parts, we used 5 years of data. We used about 20,000 different unscheduled removals, and our models predicted about 6,000 of those. So what does that mean as far as cost effectiveness? Well, this could have caused over about $20 million in pain to our operation. As Randy mentioned earlier, a 15-minute delay for us can cost us, on average, about $30,000. That's just 15 minutes. Imagine if you were had your iPhone on one of those planes that was delayed and you didn't get it till the next day. Not only does it cost us our operation, but also our customers are mad, and that hurts our brand. So we don't want to do that. So of that delay, pain that was prevented, we could prevent about $20 million in pain. And currently we have about 30,000 parts that have been modeled with this predictive modeling, and about 2,000 of them are at risk. And at risk doesn't mean that it's gonna fail today. That's another issue with sensor data, is that when your sensors start to go out of some type of trend, then you start to react. This model gives us a window of time to react, so that way we can plan our scheduled maintenance. We know that in the next month there's going to be a problem with this part, and we can wait for when that plane has a scheduled downtime, so we can make that prediction. And we also include some cost-saving measures. The way we do this is we look at the cost of this part in causing a delay, its potential cost and delay, and compare that to its repair costs. But we also prorate that repair cost by its survival probability. So if a part's survival probability is at 50%, we assume that we've used up 50% of that part's useful life. So we prorate that cost of repair. Instead of repairing a brand new part, we're repairing a part that's already used up half of its life. So that way we are being very cost effective in our predictive maintenance. And kind of after we do these predictive models, we get these results. It's kind of a screenshot of what our analysts might look at. They'll pick an aircraft that is going into some scheduled maintenance, and then they'll get a list of the parts that we predict that are at risk, and then look at the cost-saving metrics. If in the next week this plane's going to be down for scheduled maintenance, go ahead and remove these extra parts, and we think that this is going to save us pain further on. Along with this process, we also have to communicate with our actual mechanics that are on the ground doing these removals, because we're telling them, give them extra work. So we have to communicate with them, okay, it's not extra work right now, but you're probably gonna have to remove this part later. So either do it today, or do it during lunch. And no one wants to miss lunch, so we're going to do it today. So this is kind of just a screenshot of what's our back end where it's reported out to our analysts to make the decisions for them. So we talked about back testing the models. Now we put them into production in the past couple of years. And so far, this is kind of our results going to this year. In 2019, when we switched over to Databricks, you can see our increase in our savings and delays prevented have exponentially increased. And this is just with a small fraction of our parts. Our future goals will to expand these models to more parts. And just this past year, we've had almost $2 million in savings for our delays and preventing cancellations. So our vision for the future is to fine-tune these models to increase more financial benefit to them. So one of the things I talked about earlier was that infant mortality. So that's a risk that we also want to put into our financial calculations. So we're taking off a bad part on the plane. We don't want to put a bad part back onto a plane. So we want to use that probability of a infant mortality part and put that into our financial calculations to better fine-tune our financial benefits. We want to integrate these predictions into more tools so that more engineers, more analysts have this available to them so they can use that in their maintenance control. So we're seeing that, say, the model tells us this particular vendor seems to underperform. Well, maybe we need to contact that vendor, do some type of different maintenance programming. Maybe there's an issue with the position. The models tell us that we have all these different features that tell us there could be problems with maybe the position not versus this actual part. So we'll use those models to fine-tune our maintenance so that maybe this problem won't occur again in the future. We plan to also incorporate some sensor data. And the way we're using sensor data right now is more of a gut check. So we're getting telemetry data that going out of a upper control limit. The maintenance guy's getting these alerts. Then it goes to our smart time models and say, okay, we're getting an issue with this area, this system. Our predictive models will get narrowed down to a specific part that could be issue. So that previously they probably would have tried to pull off 4 different parts, but only one of them was the problem. We're telling them this specific part probably is the problem. So it's help our telemetry data fine-tune their predictions. Another project that we're working on is we call health on the shelf. So there again, we talked about that infant mortality problem. Well, why do we have sometimes infant mortality? Because our inventory system with our parts on the shelf tend to go with a first in, first out system. Well, what's the parts that go into the inventory first? Those are the ones that typically failed early. So they're failing early, we're repairing them, putting them back on the plane, and then they're failing early again. What we're trying to do is rank those parts that are on the shelf and find the best parts that are on shelf and use those first. So maybe we have a brand new part that's on the shelf, but it keeps on being put behind all the bad parts that are coming off early. So we're gonna go for that good part, that new part, and try to put that on the plane earlier before our maintenance, so it reduced that infant mortality issue. And at that, we'll open up for questions.
Yeah, so I saw you prevented essentially 40 delayed flights. I'm curious, I guess, what percentage of the total of delayed flights that you guys prevented? So I think you said 260 some odd thousand flights a year.
You're saying how many delays that we have in operation?
In terms of percentage, I think the chart showed around 40 delayed flights that you had prevented using these analysis.
So currently we're just scraping the surface on this type of programming. We have other programs that look at putting like specific hard times onto a part. So what that means is like just scheduled maintenance regardless of the characteristics of the part. One way they do this is say like if you drive your car 3,000 miles, you just do scheduled maintenance, right? You go get an oil change. Well, it could be different depending on the type, how you drive your car. If you drive it just highway miles, you might extend that out for a little bit longer. Maybe it's a newer car, so you can don't have to change your oil that often. Maybe you drive in the city, stop and go traffic, so you have to change your oil a little sooner. So all our operations look at all these different characteristics to customize it for that. That's one way we're trying to mitigate that. Like I said, it's, right now we're a small fraction of our actual delays.
Yes. Have you looked at any other data sets to join into those models? For example, in supporting some other aerospace companies, they'll often look at climate data from NASA, pollution information to feed into their prognostics. You know, there's the plane that flies in the heat, the one that fails faster than the one that maybe flies in.
We have looked at that. So he talked about including other data. Maybe climate could be an issue. Well, climate can be an issue, but at 30,000 feet, it's going to be the same everywhere. So that's not much of an issue. But on the ground, it could be different. And we have seen some models that we've seen, like windshields were cracking in the summer months. And so we're starting to notice those trends, and we realized, well, those airplanes were sitting on the tarmac in 100-degree temperature in Memphis in the summertime, and it was causing overheating issues. So there are some seasonality aspects of it that we do kind of tease out. So we'll put some time variant coefficients in there as well. So along with that, some data is an issue. One of the sensor data that we're experimenting with is a product that we provide at FedEx called SenseAware. They used this during the pandemic to ship the vaccines. As you know, the early vaccines had to be kept at a certain temperature, and this little sensor device records that temperature, records geolocation, records shocks, records humidity, and we use that to correlate a possibility of maybe dew forming inside of an aircraft. And the problem with that is if dew forms inside of an aircraft, it may be creating malfunctions on the machines, but we don't see the evidence of that by the time we actually do maintenance, because they open up the aircraft, the water is gone. So we're using that to try to calculate the possibility of dew actually forming inside the aircraft. So those are other sensor data we're trying to incorporate as well.
Thank you for the presentation. Does your model predict the time of failure?
Yes.
How does it work with the model?
I'm sorry?
How does it work with the model?
So we're using a slightly different distribution. So typically, machine learning model, you're doing a classification problem or you do a regression problem. Those regression problems are a linear distribution. As we talked about earlier, we're using that bathtub curve, which could be more of an exponential distribution. Sometimes it's referred to as a Weibull distribution. Cox proportional hazard model distributions could be also useful. So we're fitting our data to a slightly different distribution and use that as our predictive variable. What is that time to failure according to that history given the characteristics of the part?
But we use the time to failure more as a classification. I mean, we're basically saying, is a part at risk in the near future or not? We don't rely saying that we know it's going to fail in 500 hours exactly from now. So we use that, we create that prediction, but we use it more as a classification.
Hello. Okay, I have two questions. First of all, how do you know how much time a component has been used? Do you have this information?
Yes, we have that history of that individual part, how old that part is, how many times it's been installed, how many times it's been removed, and that's all the feature set that we use to build our models on.
But do you know only, for example, when it has been mounted, or also, for example, if the airplane has been stopped for 3 months and after we fly again? You know also when the component has worked.
So I think you're asking
Diminishing return on repairs? Is that what you're asking?
In the sense that it's possible that an airplane is stopped, like, I don't know, for 2 days, didn't fly. And so you know also this information?
Sure, so we'll look at different types of parts. So like landing gear is only used when you land the plane or when you take off. The rest of the time, it just sits in the airplane and it's not used. So the time it's on wing doesn't really matter. So we'll look at cycles, the takeoff and the landings, and we'll model those specific parts for that area. Other parts are maybe like a valve that is used during the flight time of the aircraft. It's used the whole time during the flight. So then we'll use the hours for the parts being used to model it. So yeah, we'll customize the model based on whatever time period we think is appropriate for that part. So sometimes it's going to be the cycles, it's takeoff and landings. Sometimes it's the hours being run. And there's other parts that we even look at how long it's been installed. So we had an issue with a part that it's called an NJP. It's the sensor that sits inside the gas, the jet fuel, and it just measures the level of fuel in the plane. So one of the issues that was thought by the engineers is that how long it sits in that fuel could cause more erosion. So it didn't matter how long it flew, didn't matter how many times it took off, it's how long it stayed in that fuel. So we looked at that as a calendar date model too. So we customize them for that.
Okay. Another question. How do you check that the component that you have changed, for example, for maintenance, is really close to the breakdown?
So we'll send it off for repair, and they will give us a diagnostic of the part. So when it comes back, they'll say, yes, this part was actually failed. There was a problem with it. We actually had a part not too long ago that was triggered because of a sensor alert. They looked at the statistical models. They said, yes, this particular part is an issue. It's causing the temperatures to be out of whack. They sent it off to the vendor. They came back, and the whole thing was wide open. The vent has been open the whole time. So it was pretty obvious that this part was actually the thing that caused the failure. So,
okay, thank you.
yeah.
I have a virtual question. Are you using a vendor to get the ideal telemetry metrics, or are you using data collected from your own fleet?
Both. We have recommended times from the manufacturer, and we use that on, when I talked about the business rules, that's part of our business rules. So the vendors will tell us what a repair would take, will last, or the manufacturer has recommendations as well. We don't, those aren't hard times, but we use them in our rules to show that the part's at risk beyond those times.
Hey, Kaplan-Meier is specifically useful for large data sets. How do you manage situations where you might not have the data required for the granularity you're looking at?
I couldn't hear that.
Yes?
Sorry, so Kaplan-Meier, the specific curve on the right-hand side, it's useful for large data sets. How do you deal with parts where you mightn't necessarily have the data?
That's a good question. So,
Repeat the question.
asking about having small sample size. We do have somewhat of a small sample size because we do have failures on the large scales, but they don't fail that often. And using this Weibull distribution, it doesn't require a huge sample size. So that's what the benefits of actually using the component history is we don't need a huge sample size to teach a machine to actually figure out where the problems are, because the problems don't happen very often. But we also use a synthetic minority sampling techniques, SMOOT, to compensate for that. So we'll create a synthetic sample set that mimics these failures that don't happen very often. So yes, we do some compensation for the small sample size as well.
Could you go into any detail about models that did not work well for you?
Classification models don't work because you can't just say, okay, tell me failure, not failure. That's not really predictive. Linear regression models aren't really helpful because, like I said, we don't have a linear distribution with these parts. They're not just failing consistently. With age, we have periods of random failures, and we have infant mortality issues. So those models weren't very effective at first.
Thank you so much, David and Randy, for being here and staying after for Q&A.
Good water.